All right, section 4 of Unit 3 is all about proofs. Before we begin, let's review a couple terms here. Remember, congruence means that things are exactly equal in size and shape. It's like saying we have the exact same triangle or the exact same square, whatever shape it is. Not only is it the exact same looking shape with all the same angles, but they're all the exact size as well. So all the sides are the same measure. Another one to recall here, CPCTC, corresponding parts of congruent triangles are congruent. The CPCTC. And that's a theorem that we use. Once you can say that these two things are congruent, so once we know this term can kind of distinguish between two shapes, then we can use this theorem as a reason. So it might be useful to kind of write this down here, that you use it as a reason in your proofs to say, okay, first I can show that these two triangles are the exact same triangle. Now I can say then, okay, these pieces are the same from those triangles. Another note with that one, you must prove that the triangles are congruent first before you can use CPCTC. And not just triangles, any shape. First, you have to show that the shapes are exactly the same size and shape, or the two figures are. Then you can say, okay, all of their parts match up. So this angle is that angle. So in this case, if FJK, if this triangle right here were congruent to PQL, so it matched up perfectly, you can kind of see, I wonder if I can flip this around. There we go. Notice that they match. But we had it like this, so we have to keep it in the right position. Well, when we flipped it, F was where P was, J was where Q was, K was where L was. That's why we have to write it this way. And the matching sides are congruent and matching angles are congruent. So this angle F, if we measured it out, is the same as P. This angle J, if we measured it, is the same as Q, and so on. So that's what CPCTC means. First, you have to show that they are congruent. Then you can say all of the parts match. So, for a couple examples here, let's identify which property will prove these triangles congruent, or which theorem. So again, ones we can use are side, side, side. If 3 sides of a triangle are congruent to the other 3 sides of a different triangle, then they're the same. Side, angle, side. And notice the angle is in between the 2 sides. Angle, side, angle. Notice the side is in between 2 angles. Angle, angle, side. Or hypotenuse, leg. This one obviously is only true for right angles. In this case, especially in our first one, feel free to test some values of angles and sides to check if things work. So if we look at how this triangle and this triangle is set up, they look pretty similar in size and shape, but we have to look at the figure. This one has 1 swoop and 1 swoop. So what it's saying is only these red ones are congruent to each other. This one has 2 swoops here and 2 swoops here, so only the green ones are congruent to each other. So if it helps, we can just kind of randomly say, all right, the red ones are 30 and the blue ones are 40, because they never actually told us what any of these numbers are. They just told us that these are the ones that matched. Okay? These sides, we have 1 here and 1 here, so those are equal to each other. And we have 2 dashes here and 2 dashes here. So we'll call the black ones maybe 3 feet, and these blue ones over here maybe 2 feet. So notice then, this triangle would be 2 by 2 with 30 degrees and 30 degrees. This would be 3 by 3 with 40 degrees and 40 degrees. So because they didn't kind of match everything up, although these are both isosceles triangles, they don't actually match each other. They're not the same. So in this case, none. Nothing would prove these triangles congruent. They're not actually the same as one another. Okay, looking at this next one, this little box here indicates it's a right angle. Across from the right angle, we have a hypotenuse, with 2 dashes, being congruent to this hypotenuse with 2 dashes. So again, those ones are the exact same. We can say they're both 5 feet, maybe, if we want. 5 and 5. Just kind of make up some numbers. The only other one we know is this side and this side. In each case, those are legs. So this one, and maybe we'll say that those are both 4. So in each case, we have a right triangle with its hypotenuse being congruent to a hypotenuse, a leg being congruent to a leg. So these are, in fact, the exact same triangles. So how do we know that? We used hypotenuse-leg theorem. If you were to solve it all out, in the end, this would be a 3, this would be a 3, and we'd have the exact same triangles. So hypotenuse-leg works for that one. Let's skip ahead to 6. 6 is pretty much the exact same as 2. So we'll just go quickly through that one. Again, right angle, hypotenuse, congruent to hypotenuse, leg, congruent to leg. So we call that the hypotenuse leg. Looking at number 3 here. Now, they haven't given us all of the information, or at least they haven't drawn it all on there. We can see this, oops, let me go further, this angle congruent to this angle. We can see that this side is congruent to this side. Now what they haven't drawn on here, some more information that we know, this angle is congruent to this angle. How do we know that? Well, those are vertical angles, so they have to be congruent. Even though they didn't draw it on there, we know for a fact that these ones are congruent to each other. So we have angle, the side right next to it, and the angle right next to that being congruent to the angle, side right next to it, the angle next to that. So this one would be angle, side, angle. These two triangles are the exact same ones because of angle, side, angle. Similarly, in number 4, we can see side congruent to side. We can see this angle congruent to this angle. And one that they didn't show us is this side is congruent to this side. It's the exact same side. It has to be congruent to itself. It's the same exact size and shape as itself. So we have side, angle, and side, all kind of right next to each other, of this top triangle being congruent to side, angle, and side, all right next to her, or to each other, of the bottom triangle. So side, angle, side is going to be that that congruence theorem. In this case, right now all we know is side, side, and the angle next to it, SSA, congruent to SSA. Well, SSA, or side-side angle, is not actually a congruence theorem. So at first, we're tempted to say none. Nothing will show that these two triangles are exactly the same. But we know from earlier, the isosceles triangle theorem says if this side and this side are equal to each other, then this angle and this angle have to be equal to each other. Well, same thing. Over here, all of these have one tick mark, so this and this are just as long as the blue sides from this triangle. So again, the angles across from them have to be the same. So if we look at it now, using our isosceles triangle theorem, we know that angle, angle, and side are congruent to angle, angle, and side of this triangle. So although at first we might be tempted to say none, after we use that isosceles triangle theorem, we can say angle, angle, side, and angle, angle, side. So these are in fact congruent triangles. So just with the information they gave us, none, but after the isosceles triangle theorem, then yes, angle, angle, side would show that they are. So that was our first 6 examples. Now we're going to get into some proofs. We're going to start with the 2-column proofs, and in the next video we'll go into the coordinate proofs. So in this case, we have a figure. Looks like 2 triangles here. This side is parallel to this side, AP parallel to LN, and PR equals NR. So from here to here is the same as from here to here. They're the exact same length. So our statements, we We always start off with what is given, and the reason why it works is because it was the given information. Okay? From there, the first thing that we can say is that angle PRA, so from P to R to A, so I'm going to draw in this angle, it's the same as N to R to L. So it's the same as this angle. We know that has to be true because these are vertical angles. And vertical angles are always equal to each other. Because vertical angles are equal, this is the same as this. Okay? I'm also, just so we can see it better, I'm going to draw in those lines. So we have an angle and a side in each case. Now this proof you can go two ways with, and I'll show you both ways. Feel free to only write one down. You can write both down if you want, but I'm going to show you two different ways. First off, we can say that PAR is equal to NLR. So P to AR right here is the same as NLR, this one here. Now what lets us say that? How do we know that works for sure? Well, if these two lines are parallel, parallel lines imply that the alternate interior angles are equal. So parallel, parallel, here's a transversal, so this one has to be equal to this one. Okay, or we can use these ones. I'm going to do these ones in red, though I've already used red, so I'll do double. These two, or this one, sorry, is congruent to this one. Oh, I'll do it with two there so you can see it better. Again, that's actually from the same reason. Because this and this are parallel, the alternate interior angles right here and right here have to be equal to each other. So at this point, we've got a lot of information on here. So we can either say, if we're looking at our triangles, this top triangle, ARP, is congruent to LRN. We can first off say that by angle, angle, side. If we used this one, that was our blue one up here, angle, angle, and side being congruent to angle, angle, and side, then we can say it by angle, angle, side theorem that these are the exact same triangles. Or let's say we didn't do the blue one up here, we did the red one. So this angle, this side, and this angle. Same thing. I wrote these in different order, but they still mean the exact same triangles. P to A to R, this triangle on top, is congruent to NLR, this triangle on bottom. Why? Because of angle, side, angle. This angle, side, and angle are congruent to this angle, this side, and this angle. So either case, these two triangles are the exact same triangle. Now, again, you can write these in whatever order. Notice the top triangle, I named it as ARP in the first case. Then I named it as PAR in the bottom case, or in the blue and in the red. And that's fine. You can use whatever ones you want. You just have to make sure you match the other triangle to it either way. So A always goes with L. R always goes with R. P always goes with N. P, N, A, L, R, and R. Either case. Now that I know that the top triangle is the same as the bottom triangle, now I can say for sure our proof here, P to A, this is the exact same length as N to L. How do we know that? Because they're the corresponding parts of congruent triangles. So they are congruent. Since these triangles are exactly the same, this side and this side have to be exactly the same. All right, let's look at another example here. In this case, we have kind of a trapezoid figure, A, B, D, C. Yes, they kind of went to A, B, D, C. We know that this angle 1 is equal to this angle 2. Actually, I'm just going to draw those in. 1 is the same as 2. We know that from A to C, this side is exactly the same length as this side. Okay, so statement 1, we always start off with a given statement. And the reason we know that all of that information is true is that was given. They told us that. So we know for sure that that information is all true. My second statement then is that AEC, so this angle, is equal to BED, this angle. How do we know for sure that those angles are exactly the same? Well, they are vertical angles, and all vertical angles have to be equal to each other. So this has to equal that. Okay, now at this point, I can look at my triangles. AEC is congruent to BED. Now I drew this out in a triangle so I can overlap it here. AEC, this triangle here, the red one, notice how I can kind of overlay it and it matches there perfectly. It's the same as this triangle over here. And to prove that or show you that, I'm going to flip this triangle around. Flip left to right. Notice how one stayed in the same place in the top corner. And when I overlay it here, it matches perfectly onto BED. Notice that 1 is now in the spot, I know it's backwards, but 1 is in the spot where 2 was. So we know that these are exactly the same, and they told us that before. They already told us that those ones are exactly the same, so they match. Okay, now that I know that AEC is the same as BED, they're the exact same triangle, I can use that information then to say that AE, this side, is the same as BE, this side. So what I'm going to do with that, I'm going to draw that in here. Actually, I'm going to erase that stuff. Let's say now I know that this has to be the same as this. Has to be, because those two triangles, these bigger ones, the ones that overlap here, these are the exact same. Okay? Oops, I should have said, we knew that one from angle, side, angle. We know this from corresponding parts of congruent triangles being congruent. They have to be. Now, looking at it, AEB is another triangle. Oops. Write it in that it matches right there. Now, we never specifically started out and said, oh, there's a triangle AEB, but we can see on the figure that it makes this triangle here. Okay, I'm going to move it away. Notice when I have this triangle here that I made, this side is the same as this side. So when I move this down here, I can draw those in, say that this is congruent to this. Okay, I'm going to do it kind of down here away from the figure to make it a little bit easier on us. So AEB, the new triangle that we just made, is an isosceles triangle. How do we know that? Well, that's the definition of isosceles. It is a triangle with 3 sides. 2 of these sides are equal to each other. Well, if those 2 sides are equal to each other, then it seems pretty obvious that this angle and this angle have to be equal to each other. How do we know that? Well, again, that's the isosceles triangle theorem. This side means this angle, this angle. Okay? Now, I don't know if these will all come with it. I bet I can grab them all. If I move these all together, overlay it on the top here, what it's saying is this angle is the exact same as this angle. What did we name those? 3 and 4. 3 has to be the exact same angle as 4. Why? It's the isosceles triangle theorem. Once I can show this is an isosceles triangle, which we did, I can say that, right, this side is the same, so this angle and this angle are the same. So we've proved that angle 3 is the exact same as angle 4. Before we get into this last one, I want to do a quick review of the perpendicular bisector theorem. The regular perpendicular bisector theorem says if a point is on the perpendicular bisector of 2 endpoints, then that point is equidistant from those points, and the angle made is bisected. So what is that saying? Well, we have our points A and B right here. There are endpoints, so they make this segment AB going right there. Whoops. Sorry about that. So, C, this point up here then, if it's on the angle the perpendicular bisector, so if this right here This green line, we'll call it the angle or the perpendicular bisector of AB, and C is a point on the perpendicular bisector. If I was to draw a line from A to C and C to B, those lines have to be exactly the same length. We'd say this length is the same as this length. Okay, if I continued, oops, a little bit off. If I continue this line way down here and I put, oops, a dot right here, same thing, drawing from here to here and here to here, this line has to be the same as this line. Because it's on the perpendicular bisector, it has to be exactly the same distance from each endpoint. Also, this angle from here to here is the same as this angle from here to here. Okay, so if we kind of, oops, smartboard getting off. If I were to draw my angle bisector right there, these two angles have to be the exact same. Okay, it's the angle created is bisected. So that is perpendicular bisector theorem. The converse of that, though, so if I do it the opposite way, if I didn't know that this line was the perpendicular bisector, but I know that there's a line from C here down to the segment AB, and I know that C, if we were to measure it out, and we have this length and this length, and we were told, well, they're the exact same length. Maybe they're both 4 feet, maybe they're both 20 centimeters, whatever it is. If I know that they're the exact same length, then this point has to be on the perpendicular bisector. Okay? If you can draw a line straight down and make it perpendicular, that line is the perpendicular bisector. Okay? As long as this and this are the exact same length, then C is going to be somewhere on the perpendicular bisector of AB. We're going to need to use that information in this next proof here. Okay, so if we're given this figure, y, x, w, z, kind of big kite looking thing, with this intersection in the middle, O, so from y to w, x to z, where they meet is that spot O. We know that y to x equals w to x, so these two are the same. We know that x or z to x bisects the angle y, x, w. So I'm just going to draw in that information real quick. Make those ones same. This angle is the same as this angle. So our first statement is, again, all of the given information. What can we say from there? Well, we can say that angle YXO equals WXO. Again, definition of angle bisector. They told us that. That's why we can draw that in, because it bisects those two pieces. I can say that from X to O is the same length as from X to O. So I just kind of draw the lines right there. Those are the exact same lengths. Why? Well, that's the reflexive property. Anything has to equal itself. Now, looking at these triangles, I have YXO and WXO. Red line, green angle, blue line or blue side. So those two triangles are exactly the same. YXO is congruent to WXO. How do we know that? By the side angle side congruence theorem. Okay, so we know that those two triangles are exactly the same. Now that we've shown that they're the exact same triangle, we need to show some additional information. Y to O is the same as W to O. And we know that because they are corresponding parts of congruent triangles. So, erase that information and I'll say this has to be just as big or just as long as that. Same thing, this one and this one are just as long as each other. Now, X, right here, it's equidistant from Y and W. O is equidistant from Y and W, right? So O we can say is the midpoint of YW. There's a straight line here. This is this is exactly the same as this. So O is the midpoint of YW. If O is the midpoint of YW, because it's the definition of a midpoint. And x has to be on the perpendicular bisector, then this line, x down to O, or it looks like it keeps going, x to z, is the perpendicular bisector. So y to w, that's our segment, x down to O, or you can even go further and go x down to z, that is the perpendicular bisector. So I can draw in, if I want, right angle here. Okay, that has to be our perpendicular bisector of this segment. Why can we say that? How do we know that? Well, again, that was the converse of the perpendicular bisector theorem. Because this point is the same distance from each of our endpoints, and this point is the same distance from each of our endpoints, then these 2 points, if we connect them together, make the perpendicular bisector. And if we can continue that on, it matches up with z down here too. So this whole line, that whole line there is the perpendicular bisector. So if this is all a perpendicular bisector down to here, what can we say from that? Well, yz, this length, has to be the same as wz. They have to be exactly the same length because, again, using perpendicular bisector theorem, if this point is on the perpendicular bisector, then it is equidistant from the 2 endpoints. So these have to be the same length as each other. So yz equals wz. And we've now proved what we were setting out to prove.